Okay, so what I wanted to kind of start or talk a little bit more about is functions and parameter passing. And for sake of example, let me just start with something where we're printing a couple of numbers in a string or something. Okay, so let me make some data and text, and then I'll have global main and main. And then, of course, what are our first two commands? Store pair x29, x30, stack pointer, -16, exclamation mark, and load pair x29, x30, stack pointer, and 16. And then we need to move W0 with the immediate of 0, and then return to the operating system. Okay. For the data, let me just do, let me just make a format string. Doesn't have to be anything in particular. So let me just say, let's call this out string, whatever. And this is ASCII, so it's a null terminated ASCII string. And let's just make it the first number is %I, the second is %LI, and then I'll put a carriage return in. Okay, so accordingly, like if I were to call printf with this in C, I would call it as printf, then the name of this string, then the first number, then the second number, right? Okay, what type is the first number? It's an integer, okay, which means specifically it's a, how many bits? 32-bit integer. Okay, so just an int, right, in C is 32 bits. An LI is a long int, right? Okay, so 64 bits in that case. And the reason I chose to do one that's 32 bits and one that's 64 bits is just to illustrate what is going to happen in a second. Okay, so if I wanted to call printf, I need to do this, okay? Now in C, what I would be doing would be printf, and then I would have the name of my string, my first number, and my second num, okay, whatever values those are, okay? Okay, so let's just pick values for my first number and my second number. Doesn't really matter, but let's just pick something. Pick a couple numbers. 7, and how about 1832? Yay, okay. So if I wanted to do this, okay, in order to set up the call for printf, I have to pass parameters to it, right? And the parameters that I need to pass to it are the location of the format string, the number 7, and the number 1832. Yes? Okay. Where is the format string? It is in memory someplace, right? How do we find out where it is? Hmm? Right, so a pointer, right? And in this, what we'll do is, what did I call it, outstring? That. So I'm going to load x0 with the address of that format string. And remember, in at least this assembler, the syntax is the equals outstring means the address of it. That's kind of like the ampersand operator in C. I don't know why they chose a different symbol here, but whatever, right? Okay, so what that instruction on line 13 is going to do what? What's going to end up in register X0? The address of the format string, whatever it is out in memory. Okay, now, if I want to print the numbers 7 and 1832, parameters have to also get passed in registers or by pointers, okay? Or so, uh, Okay, so the difference here, right, is passing an object by reference means to pass a pointer to it. Okay, and that's what we're doing with this string, right? I can't pass the string by value. I can't fit a string into a register, but I can fit its address. Okay, now for the numbers 7 and 1832, can I pass those by value? Yes, which means that, and the reason I can do that rather is because do 7 and 1832 fit into registers? They do. They're just numbers. Okay. So I need to put 7 in a register and I need to put 1832 in a register. Which registers do I need to put them in? Okay. 19 and 20 if I wanted to kind of preserve them, but if I want to pass them to printf, which ones do they need to be in? 1 and 2. Okay. And in this order. Okay. So notice two things. Why did I put 7 in a W but 1832 in an X? Right, W is a 32-bit register, X is a 64-bit register. Okay, and again, just to make sure we're clear, W1 sits inside of X1. They're not physically separate entities. Okay, what was our analogy for that? Yeah, a small bucket inside of a big bucket. Okay, you got the 2-gallon bucket inside of the 5-gallon bucket. Um, Right, okay. So the W registers are the small buckets and the X registers are the big buckets, but the W1 sits inside X1, okay? And I picked W1 here because what kind of data did I choose for my first number? I chose it to be a 32-bit integer, whereas what did I choose for my second number? 64-bit, okay? And I just picked those for sake of demonstration. Okay, so the convention on parameter passing in Linux with ARM is this. The parameters get passed in registers X0 through X7. Okay, so that allows you to pass basically up to um, 8 parameters, which is enough for most purposes. Okay, if you need to pass more than that, then you have to start using memory, and we'll talk about that later because that significantly complicates the conversation. Okay, but if I want to pass parameters back and forth, I'm going to use registers X0 through X7. Okay, what this means is that those registers are volatile, meaning that when right before I call printf, what's in the 3 registers? Whatever the address of the format string is, the number 7 and the number 1832. When I come back after printf is finished, what's going to be in those registers? Who knows, right? Not the same thing, okay? A function, printf is a function, is not obligated to preserve the contents of those registers. So if I needed to store the number 1832 for some future computation or posterity, then I would need to do one of two things. Keep a copy of it in a non-volatile register like X19 or 20 or 21. Okay, so that's option number one. Or store it in memory someplace. Okay, one of the two. Okay, but I'd have to keep a copy of it or store it someplace that's not going to get messed with by a function. Okay, and the calling convention for functions on Linux on the ARM platform is to use the first 8 registers for parameter passing. Okay, good. Okay, so that's why I put them in this order. Because what was my string? What has to go first? Obviously, is the address of the format string. Like that's always the case for printf. Okay, but what about what was my format string? What did it look like? I had %I and then %li. Yeah. So that meant that the 32-bit int would be given before the 64-bit int. And so I'd have to pass them as 7 and then 1832 because that was the order that they appeared in the format string. Yes? What kind of data is a long int? Or sorry, an int? Where does that go? 32-bit registers. And what about 64-bit numbers? To the 64-bit registers. Okay, so does this make sense why I put them in that order? All right, now isn't that logical? It's exactly the same order as A, the order that we do this in C, and B, the order that they appear in the format string, right? That's a very logically chosen order, right? We just didn't pick it willy-nilly. We? No. Okay, so let's make sure that this works. And let's see, any other questions before I assemble it and whatnot? Yes. Yes. Okay. Now, that said, if you have, so you can't mix apples and oranges in the sense that, like in C, could you add an integer and a long integer? Sort of. Okay, but technically no, because an integer is and a long integer have different number of bits, right? Okay, so if you wanted to, like, let's say that you wanted to treat 1832 as a 32-bit integer, we would have to basically do a data conversion. And we'll talk about that a little bit later, but also why you can't mix the apples and the oranges, okay? Because that's kind of a technical point, okay? Um, okay, so yeah, and the reason I picked integer for one and long integer for the other was just for the sake of demonstrating that I need to use X's for 64-bit and W's for 32-bit, okay? Good? All right, so let's assemble it and make sure it works right. All right, so I need to assemble functions. Well, okay, I'm going to go ahead and assemble it with the debugging flag enabled so that we can use GDB to kind of step through it. And I call this functions 2, not functions. Oh, forgot the S. There we go. Okay. All right, so now we have our executable file for the functions 2, and let's just run it real quick. And sure enough, there it goes. The first number is 7. The second is 1832. Excellent. Okay, yes. Oh, it makes it a comment. So um, this, like, this is how I would have written it in C, right? And the 2 slashes in front make that a comment, so it's just ignored by the assembler. Um, It did. It should, and it should turn this green color, and I'm not sure why it didn't in that line, but it's just a comment. Yeah. Um, so, like, I actually let's say that I put this on a separate. Oops, on a separate line. I think it'll change that color. Yeah. Okay. I don't know why it's not doing it when it's on the same line, but um, huh? Ah, that would do it. Okay. Yeah. Okay. But anyway, it's going to ignore it. It's just not highlighting it. with the color. Okay, so yeah, good question. All right, so I've got it works first off. Okay, so that's a good thing. And then let's actually go through and run this in GDB. So GDB functions 2. Okay, I'm going to break at main. I'm going to run, and then I'm going to step. Okay, so if I look at the registers before basically anything has happened, okay, here they all are. What's in register 0 basically when the program starts? The number 1, okay? What's in registers 2 and 3? Something, right? But this is basically gobbledygook. It's just garbage data that doesn't mean anything. Okay, and so if I just called printf as is, we would get a seg fault because what's in register 0 here? The number 1, and if I called printf, where is it going to go look for the format string? In register 0, it's going to look in register 0, say, hey, this is a memory address. It's going to go to that memory address. And can it go to memory address number 1? No, das ist verboten. Okay. So, and then of course, those two numbers are just garbage. They're not what we wanted to print. But if I step, and so I just executed by hitting step the command, this one. So what should be in register 0 now? Okay, the address of the format string, which is, okay, whatever it turned out to be, 48A048, whatever. Okay, just some memory address. Okay, but what is in X1 or X2? Still that garbage. Okay, and if I step 2 more times, what's in my registers? Okay, the first one has the format string's address, okay, whatever it was. The second one has the number 7, and the third one has the number 1832. Okay, now, here's one case where we need to be a little bit careful. What is this displaying for us? It's displaying all of the X's, correct? But the number 7 was really a 32-bit number, okay? And we'll talk about this a little bit more, but you can extend a 32-bit number to a 64-bit number. You can't always go backwards, obviously, because you'd lose information. But the way that extension works, you have to be a little bit careful. Okay, so we'll talk about that a little bit more later. But do we agree that if 7 is in the little bucket, it's also in the big bucket? Yeah, okay, we'll come back to that issue later. Um, and of course, why do we see 728 there? Well, that's 1832 in hex. Okay, yeah. So, all right, good. And so now all 3 parameters are where they need to be. And if we call printf, which is the next operation, then it prints them, and yeah, everything's glorious. Okay, good. Oui ou non? Oui? Okay. Très bien. Okay, and then we'll quit. Okay, so let's go back to our function or our program. And let's actually write a second function. Okay, now strictly speaking, we have used a function here, namely the print function. Yes? Okay, so, but let me just write a silly function that's going to do the following. Okay. So I'll write a function that's going to basically do this. Let's do long int myfunc, long int A, long int B. Okay, and let's just say there. Okay. So all I'm going to do is write a stupid function, and in C, the way I would do this would be to define a function as taking in two long integers, so two 32-bit numbers, or sorry, 64-bit numbers, adding them together, and returning a 64-bit answer. Okay. Now, I would never actually use a function like this. I would just directly add the two things. But the reason I want to do this is to illustrate, again, more about this parameter passing. Okay. Okay. So that's what I want this thing to accomplish. Okay. And then we'll modify our print stuff and whatnot to do two things. One, to call our addition function, and then two, to say the sum of blah and blah is blah. Okay, so I'll give it two numbers, like, I don't know, 5 and 7. The function should then add them and we'll get 12. And then we want to print the sum of 7 and 5 is 12. Okay, nothing particularly exciting. Okay, so the parameter passing part here is, so how many pieces of data does my function need to take in? Two pieces of data. And what kinds of data are they? Long integers. Okay, that means in terms of registers, they should be X registers because they're 64-bit numbers. Okay, and the parameter passing convention is that the first one needs to be passed in X0 and the second one in X1. And if there was a third one, it'd be in X2 and X3 and so on. Okay, so the inputs start in X0 and go in order however many you need. Okay, and if you need to use W's or whatever, then you do so as you go. And then we also are going to return something, yes? Okay, where are we going to put that return value? We got to put it somewhere in X0. Okay, so the convention is the parameters coming in go starting with X0 up through X whatever you need. And then the parameters coming out go in X0 and as many further as you need. Okay, so does that feel bad in some way or annoying in some way? Okay, why does that feel annoying or bad? Yeah, we're reusing a register for multiple reasons, okay? Which means if there's data in it that we needed to keep, we've got to stash it someplace, okay? Someplace safe. And that's annoying because that's work to do, right? We have to consciously think about putting this data someplace. Any other reason that that feels maybe annoying? Okay, yes. So, and we're going to see exactly that issue. Okay, so Jaden's point is, well, what happens if you use a function and then you need that data for some other function? Then you're going to have to move things to and fro. Okay, and yes, is it annoying? Yes, but as they say in Poland, Towski Shitsky. Okay, they don't actually say that in Poland, but yeah. That's the convention, okay? And we just have to stick with it. Now, maybe a better question is, why does a convention like this need to exist? Well, one of them is, how many registers do we have to work with? 32, basically 32, right? There are 32 registers. Some of them have, of course, specialized purposes that we're not allowed to really mess with, but 32. Now, that's a lot, okay? But if we kind of go back into like old school processors, okay, so how many registers are in the processor that's in my Commodore? 3. Okay, there are 3 registers: the accumulator, X, and Y. Okay, that's it, right? And so what that means is if you want to be passing parameters, you have to have a very, very well-defined convention as to what goes where. Okay, if you don't have a whole lot of registers, now on Intel, for example, the earliest chips, so like the 8086, I guess, had basically 4 registers, and they were like A, B, C, and D. And Intel's a little bit weird in the sense that certain operations expect the registers or certain operands to be in certain registers. So, for example, let's say that you wanted to add 2 numbers. The 2 numbers to be added would need to be in registers A and B, and the output would go to register C. Okay, I don't know why they did it that way, but they did. Okay, in our case, in our architecture, we can add together any 2 registers we want and put the answer into any other register that we want. In old school Intel, it was hard coded to put the answer in register C. Why they did it that way, it probably simplified the circuitry a little bit, but you know, we need a time machine to go back to the 1970s. Okay, so we're on ARM and we're using Linux. Okay, so it's really a combination of those 2 things. Linux enforces a particular ordering of the registers for the ARM chip, right? We're doing Linux on x86, different convention. Okay, but we've got a particular hardware platform, we got a particular operating system sitting on top of it. Thou shalt respect that convention. And if thou dost not, woe unto thee. Okay? All right, so what is my stupid little function supposed to do? All it's going to do is add 2 numbers. Okay? So, for reasons that will become clear later, okay, I'm going to go ahead and do like we did at the beginning of the program and the end of the program. Now, strictly speaking, it won't be necessary in this example, but it will be later, and so let's just get ourselves ready for that, okay? Essentially, this store pair, load pair thing is, what was our analogy for that? And we'll see the details of how it works later. Right, we've all read Hansel and Gretel, right? Okay, so what was the story, right? Hansel and Gretel go wandering off into the forest, and they leave a trail of breadcrumbs as they go so that they can turn around and follow that trail of breadcrumbs back and get back to where they started from. Okay, essentially this store pair, load pair, ret thing is kind of going to be part of our breadcrumb system. Okay, okay, so let's just say here, okay, so parameters come in, data goes out, and the convention is the parameters come in the first 8 registers, and the answers go out in the first however many registers. Okay, so for us to call this function properly, we need to put the first number in x0, the second number in x1, and then the answer will go out into x0. Okay, so how do I add 2 numbers? Well, what do you think? Yes, how about we just add 2 numbers? Okay, and where are we putting the answer? X0. What 2 things are we adding together? X0 and X1. Okay, could I have written this as X1 comma X0? Yes, because addition doesn't matter the order, right? Whereas if I were subtracting, could I write them in the opposite order? No, because that would change the answer. Okay, so this is all my function's going to do is just add two numbers. Okay. All right, now let's go back to our main function. And let me change my format string to the sum of %li and %li is %li. Okay? Yes? Okay, so first thing we need to do is compute the sum of the two things, the two numbers. So what two numbers did we want to add together? Let's do 5 and 7, and then let's okay, so we'll do 5 and 7 just for sake of example, right? The sum of which is obviously 12, right? So we should expect to see that. Okay. Now, how do I call my addition function? What did I call that function? I named it myfunc. Okay. So I need to branch and link to myfunc. Okay. The L that's in that, so branch and link, the link is part of the breadcrumb system, which again we'll talk about later. Okay. Okay, good so far? All right. When I return out, so on line 16, after myfunc is run, what data is where? 12 will be in X0. 5 is just gone. And 7 will be still in X1 because I never changed it in my function. Okay, but as far as we're concerned, 7 has also been obliterated. Okay, so if I want to preserve these two numbers for future use, what do I need to do? I need to put them someplace. Okay, someplace safe. We have two options for someplace safe. What are the two options for safe places? Memory, because we got oodles of that, or non-volatile registers, which would be 19 and up. Okay. For sake of demonstration, let me put them in memory this time, just for giggles. Okay. And actually no. Yeah, I'll go ahead and put them in memory. Oh, okay. It looks like the reason it didn't work there is I have to have two spaces. Well, that's weird. Because here I did it and it worked. Maybe. Huh, that's weird. Okay, so I'm going to stash X0 and X1 on this thing which is called the stack, and we'll talk about what that means later. But the stack is really just a special part of memory. So think of it, I'm stashing those number off into memory. Now they're still in the registers, so when I store them, I'm basically stashing a copy of them into memory. Okay, so when I come back, what is in X0 when the function finishes? Sorry, before that, before we print, what did myfunc do? Yeah, the result. So what's in X0? The number 12. Okay. If I want to print the sum of blah and blah is blah, where does the number 12 need to be for the printing? X3. Okay, why X3? For printing, what has to be in X0? Address of format string. What has to be in X1? The first number. X2, second number. X3, third number, and so on. Okay, in this case, that's all we've got. So our number 12 is currently, when this addition function finishes, sitting in register 0. Where do we need it to be? 3. Okay, can I move it from 0 to 3? Sure. Okay, so let's move x0 to x3. Okay, and remember, in most of these instructions, you write the destination first, not last. It's just the way that they did it. Okay, I didn't make that up. Okay, so that moves x0, the number 12, to x3. What do we need to have in x1 and x2? What were we trying to print? Yeah, our two long integers, the things that were our inputs. So it was what, 5 and 7? Okay, so where are the numbers 5 and 7 currently stashed? This someplace over in memory. Okay, so I need to pull them off of the stack, basically retrieve them from memory. And the way that I'm going to do that is load pair, and I'm going to put them where? X1 and X2. Okay, because where do they need to go for printing? Yeah, they need to go to, so let me put some spacing in here. Okay, so what if I want to call printf with 5, 7, and 12, okay, 5 and 7 were the two numbers I added together, 12 was the result I got from my addition, okay, what has to be in which register? What has to be in register 0 when I call printf? Address of the format string. Have I put the address of the format string in X0? Yes. Okay, line 21 did that. What has to be in register 1? The number 5. Have I put something into register 1? Yeah, I pulled it out of memory. Okay. What about register 2? Have I put something there? Yeah, the other number. Okay. And where does the number 12 have to be to print? Register 3, because it's the third number. Okay. Have I put that into register 12 or 3, excuse me? Yes, by copying it. Okay. So right on line 19, what is in register 0? The number 12. Right. So remember, what does move really mean? It is. Okay. So X0 is still, so after line 19 executes, register 0 and register 3 both have the number 12 in them. But then after line 21 executes, what happens to what's in register 0? It's no longer the number 12, but now it's whatever the memory address is for the format string. Okay. The format string? Oh, yeah. Okay, so my func, right? Two breadcrumb instructions, and all it's doing is adding, right? It's the world's stupidest little subroutine. Okay, but it's a good, at least, demonstration of a subroutine call. Okay. Like I said, we'll talk a lot more in detail about this breadcrumb system because it's important in like really, really important. Okay. It's what enables us to do things like recursion. Huh? Well, you, to understand recursion, you first have to understand recursion, Patrick. Yeah. Yeah, when I told that to my 101 students yesterday, they were not amused. They're like, wait, what? Not yet. So on Wednesday, tomorrow, I'll do the Google thing to start, and then I'll give them the Towers of Suffering. Yeah. Okay. All right. Good. Okay. So any other questions before we assemble and run this through the debugger and kind of see how this is working? Oui ou non? All right. So let's assemble it and see what happens. All right. So save. Let's assemble. Let's link. And then let's run it first just to make sure that everything goes okay. All right, that's good. The sum of 5 and 7 is 12. What I hoped to see. Yeah? Okay, now for the fun part. Let's step by step go through this in the debugger to make sure that we understand what data is where, when. Okay? Okay, so let me step through the instructions and let's go here. All right, so what is in the registers right after I executed my first two move instructions? 5 and 7, my two input numbers. Okay. And so those were just numbers I picked. Those could have been numbers that we had, scanf retrieve for us from the user. They could have been things that we pre-programmed. They could have been something we stashed in memory, whatever. I just picked numbers. Okay. Now, what's the next instruction that I'm about to execute? Is this stashing a copy of those two numbers on this stack thing. Okay, so let me show you what the stack is. Okay, so if I do that, okay, what this is going to do is show me what is currently in memory, starting at whatever address I specify. And the address I've specified is this thing called the stack pointer, which its current value is 7FFFFFEF90. Okay, whatever. And what do I see on the stack? Well, there's some stuff. And in particular, you see these two things here, or this 64-bit number there, blah, 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 EFA0, that matches what's in X29. And the reason is because what did I do? What was the very first instruction I did in my program? Yeah, the breadcrumb thing. Store pair X29, X30 to the stack. Okay, so what was in X29 and X30, it still is there. I have stashed that onto the data stack. Okay. All right. I'm about to expand the stack and stash two other numbers on it. So if I step and then I do that, the stack has expanded. Okay. And now how I told the stack to expand, I'll explain later. But right now, the stack starts here. And what do I see on my stack? 5 and 7. I also see the stuff that was on the stack beforehand, okay? So I've added data to the stack. I've basically just shoved some data out into memory. Okay, now the stack is a very special kind of, or it's a special segment of memory that we have to be very careful with how we utilize. And just as a preview of coming attractions, the way to think about the stack, I mean, how many of you guys have, did CS-211, have done that, right? Did you guys talk about stacks in 211? Okay. And what do you worry about there? First in, last out, last in, first out, all of that sort of thing. Okay. So think of the stack as a segment of memory. Okay. And it's kind of like, you guys know in a cafeteria, there's that giant, like, spring loaded plate holder, right? And like maybe you have these in your frats to hold the plates, right? And I'm sure they have them over there at Sparks. And you push a plate on, and then there's a stack of plates underneath of it. And then if you wanted to get to the plate at the bottom, what would you have to do? You'd have to pull all the plates off at the top, right? So there's sort of an ordering issue that you have to worry about. We kind of have to worry about with that here. We'll talk about that in more detail. But point being, all I've done is I've added some data to my stack, and it was the numbers 5 and 7. Okay? Great. All right, so what is in register 0? What's in register 1? Okay, so 5 and 7 are in the appropriate registers, and we are ready to call the function myfunc. Okay, so that's what's about to get executed. Okay, myfunc is going to leap its set of breadcrumbs, and then it's about to do an addition. It just did the addition, and now let's look at the registers. What's in register 0? 12. What's in register 1? Why is it 12 and 7 now instead of 5 and 7? Well, because what did I tell it to do for the addition? I told it to put the answer in register 0. Okay. And I'm about to pull off my breadcrumbs. Okay, fine. Oops. Okay, and return, and that takes me back to the main function. And if I look at the registers, what do I see? 12 is in the first one, 7 is in the second one, and what am I about to do? What command is, or what instruction's about to get executed? Oops, sorry. Yeah, I'm going to take what's in register 0 and copy it over to register 3. Okay, so if I do that, what's in register 0? 12. What's in register 3? What's in register 1? 7. And what's in register 2? Garbage. What do I want to be in registers 1 and 2? 5 and 7. Okay, and those are going to get that instruction I just executed. There they are. Okay, so I took my two numbers off of the stack, okay, into memory, or from memory into the registers, and in fact, my stack has shrunk, right? So that's like I pulled a plate off of my magic plate pusher thing. Okay, and that data is now in our registers, and there they are. Okay, so do I have everybody where it needs to for printing? Not yet. What's the one thing that's missing? The format string. Okay, so the instruction I just executed before I did any of this was that. What is this going to do? Load the address of my format string. All right, so what's in the registers now? What's in X0? Address of format string. What's in register 1? 5. What's in register 2? What's in register 3? 12. What's in any of the other registers? I don't care, right? They're not needed for now. Okay, and then I print, and lo and behold, the sum of 5 and 7 is 12. Pick up a breadcrumb, move W0 0 to that, return to the operating system, and the function finishes. Okay, so parameter passing 101. right? How do I pass parameters? They got to go in order. Second thing, functions, subroutines are not obligated to preserve registers X0 through X7. They might, but it's not guaranteed. Okay? And as such, if you need to preserve that data for future use, you have to put it someplace safe. And where are the two safe options? Memory someplace or non-volatile registers, so like X19 and so on. Okay. Now, what exactly you choose, that's up to you. Okay. Now, this sort of begs the question, why have I been so anal about preserving or sorry, adhering to this calling convention for my silly little function when it's I wrote the function and I wrote the program? Does it really matter what registers I use if I'm in control of everything? I mean, other than the printing, right? No. Could I have put the first number in register X13 and the second number in X25? Just pick them kind of out of thin air? Okay, yes, I could have done that, and it would have worked. Here's why I didn't. Okay, other than because I'm a jerk face. Okay. Let's say that I was writing my func, and my intent was that somebody else might also use this function in some of their programs. Or maybe even Linux needs to use it. If we don't all agree on a convention for what needs to go in what registers, then can we mix code with code we've written with code other people have written? No. So that's the reason why, even though it wasn't necessary to respect the convention for our example, thou shalt respect the convention. Okay? And I've got my stick over there in case any of you guys get, you know, argumentative about that. Okay? Right. Okay, so for example, printf, right? Printf expects things to be in the registers the way we've said they are. And if we deviate from that, then it would mean that we couldn't use printf. Well, I think you guys would agree that's a bad thing. Okay. And furthermore, so let's kind of back up a second. Does anybody sit around and handwrite assembly unless they're in this kind of class nowadays? Okay, not for an entire program. Okay, nobody writes entire programs in assembly anymore. Okay, so what do they write programs in then? If they're not writing them all in assembly, then what? Well, C or something. Okay, hmm? Not functional programming. Oh, they write them in lambda calculus. Don't you love lambda calculus?
No, lambda calculus shouldn't exist.
Okay. No. So for example, like let's say that I'm writing like a video game. Okay, video game engine. All of those, the modern ones, they're and even the old ones, they're all written in C or maybe C++ or C sharp. Okay, so like the original Doom and Quake engines, those were all written in C. Uh, Unreal Engine is written in C++. Unity is written in C sharp. Okay, but basically they're all C derivative languages. Okay, so nobody in their right mind is going to write an entire program in assembly anymore, like like a real world deployed thing. They're going to write in C. Well, what is C going to do? You type some stuff of code in C, and then what does the compiler do? Turns it into assembly, passes it off to an assembler, and the assembler turns it into actual executable code. Okay, so the calling convention is necessary so that the compiler knows how to turn it into the assembly properly. Okay, so there's that. But also, um, is it possible to mix C and assembly? So could I have a big program written mostly in C, but I have this little section of it that I wrote in assembly? And that is something that people still do today. Okay, is the most of the program will be in C, but parts of it might need to be in assembly. Okay, now this begs the question, why? Do they do that just to torture themselves? To have to do some stuff in assembly? No, Lord, no. Okay, so then why would you do that? And let's take a game engine as a maybe a really good example of this. Okay, so there's that, but the real reason is efficiency and speed. Okay, nothing beats hand tuned assembly. That's the fastest code that you can get this side of the Mississippi. Okay, um, C that you write and compile might be less optimized for a very specific thing. And if you've got a very specific chunk of code that needs to run as fast as humanly possible, then you need to go in and start hand optimizing it in assembly. Okay, so that's where people do this. The other reason would be in debugging, that they'll be able to look at assembly, and in security kind of stuff to track down like weird security bugs and whatnot. Okay, um, right. But if you're going to write something in assembly, in order to mix it with C, thou shalt respect the platform's calling convention. And because we're on an ARM hardware with Linux as the operating system, we have a particular calling convention, and thou shalt respect it. Okay? And if you don't, then you get the stick and things won't work. Okay, good? All right, so um, let me switch gears to something that's going to seem to have nothing to do with this. But may I change one of the numbers from 5 to something else? Sure, right? Why not? How about -1? Perfectly good number, right? And what would the sum therefore be? 6, okay, because well, that's subtraction. All right, let's make sure that that works. Oops, damn it. There we go. Okay, we got 6. No big deal, right? Let me change it back to 5, just for the moment. All right, now I'm going to assemble it this time, but I'm going to assemble it to a listing file. And what I want us to look at is how this instruction is actually encoded. Okay. Okay, so all of the instructions are encoded in, how many bits does it take to encode an instruction on this particular architecture? 32. Okay, every instruction, asterisk, but basically every instruction is a 32-bit number. Okay, now that 32-bit number needs to have several pieces of information in it. Okay, for example, if I want to add 2 registers together and output that answer to another register, I need to specify actually 4 things. The fact that I'm doing addition, the name of the first register, the name of the second register, and the name of the destination register. 4 pieces of information. Then I've got to cram all of that into 32 bits. Yes? Okay. So my question for you is, how do I write the number 5 using 64 bits? in binary? Well, I need a 4 and I need a 1, and then I need a crap ton of zeros. Okay, how many total bits are there? 64. Can I fit 64-bit numbers into 32-bit operations? Of course not. I can't even fit 32-bit numbers into 32-bit operations. Okay, so the number 5 that I've specified there is actually gotten truncated. And is that okay? Yeah, because what is there? Just a bunch of zeros. And does it matter if I chop off some zeros? No. All right, better question. What is -1 represented in 64 bits? Mm-mm. It does start with 1. So this is what was the number 5? Okay, -1. 64 ones in a row. -1 is all ones. You guys don't believe me, do you? All right. This is why I've got the iPad ready. So let's talk about how integers are encoded. Now, some of you took CS-101. And so some of you should remember this. Glare. A year and a half ago. A year ago. Yeah. Next to forget. You're going to have a fun time with comps, my friend, or your midterm next week. Yeah? Which I will post stuff on Canvas hopefully tonight. Yeah, about your soul crushing midterm. Huh? A nice, fun, soul crushing midterm to torture you? I'm kidding. I'm not trying to make it soul crushing. Okay, so how are integers actually encoded? Well, let's take the number 5. How did I know that 5 was going to be 1, 0, 1, and then a crap load of zeros? Well, how does binary arithmetic work? What are the positions, right? The place values. I've got 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and so on. Okay. Now, how do I know that it's that? Well, binary means base 2, yes? Okay. If I wrote down the number 1832, what does this mean? This means 1 times 10 cubed plus 8 times 10 squared plus 3 times 10 to the first plus 2 times 10 to the 0. Right? That's what place value means. Now, do you have to think about 1832 in this expanded form to understand what 1832 means? Like what the digits represent?
No.
No. Why not? Because you've been doing this your entire freaking life, right? But if I write down a number in binary, you do have to think about it because you haven't been working in binary your entire life. Okay? But the system is exactly the same. It's just base 2 instead of base 10. Yes? Okay, so this begs the question, how do I represent negatives in a system where there's a fixed number of bits? If I wanted to write negative 1832 like I was in grade school, what would I do? I'd put a little negative sign out front. But we have a problem on the computer. I can't just put a little negative sign out front of a binary number. There is no thing, right? So I have to represent numbers, ints, using a system that allows me to encode both negatives and positives. And the system we use is called 2's complement. Okay, to demonstrate how this works, I'm going to do a magic trick. Give me a two-digit number. 17. Okay. Base 10 number. Right? Okay. Give me another number that's smaller than 17. 4. Sounds great. The difference of those is 13. Yes? Okay. That's not the magic trick. Magic trick is this. Take the number 0, 4. And what I'm going to do is I'm going to pair up all the digits. 0 I'm going to pair with 9, 1 with 8, 2 with 7, 3 with 6, 4 with 5. And so I'm going to take my number 4, 04, and I'm going to write it as 9, 5. Okay? I'm going to add 1 to that to get 9, 6. And then I'm going to take 17 and 9, 6, and I'm going to add them. 7 plus 6 is 3. Carry. What's 1, 1, and 9? 11. And then I'm going to throw away a final carry because my numbers were two-digit. And look. Yeah.
Where are you getting this the 9, 5?
Okay, so I'm thinking of the digits 0 through 9 as being grouped in pairs. 0 pairs with 9, 1 with 8, 2 with 7, 3 with 6, 4 with 5. So I have 0, 4. Who is 0 paired with? 9. Who is 4 paired with? 5. Then I added 1 because that's part of the trick. Okay, and I got this number 9, 6. I added it to 17 and I got the correct answer, assuming that I discard that final, that extra carry. Okay? Yeah? It's crazy? Okay. This is exactly how subtraction works, or thinking about negatives on a computer, except we're doing it in base 2 instead of base 10. Okay, now the other business here is you guys might be bothered by the fact that I threw away that carry. Okay, the reason I did so is because I started with two-digit numbers. Yes, and I arbitrarily am going to declare that my answer shall be a two-bit or two-digit number. Now that may seem a little bit silly because 2 digits is not a whole lot of them, but was there anything special about the fact that I did this with just 2 digits? Could I have done it with 5 digits? Would have been a little bit more work, but could I have done that? Okay, so the reason that I restricted the number of digits and held that number fixed was so that when we translate this to the computer, the translation makes sense. Because on a computer, how many bits do I have? Either 32 or 64, it depends. Okay, but point being, there's a fixed number of them, right? In the same way that in this silly example, I said there shall be exactly 2 digits. If I had said there shall be exactly 10 digits, the same trick would have worked. 10 digits is maybe good enough for government work. Well, for most things with the government, maybe not with the budget, but, c'est la vie. Okay, so I claim that -1 is represented by all ones in this binary system. Okay, here's how I'm going to demonstrate why that's true. If I have the number 1, would we agree that in binary it should be this? Okay, I claim that this number represents -1. Okay, if this is at all reasonable, what should happen if I add the two things? I damn well better get 0. Yes, and if I don't, then something has gone horribly wrong. Okay. All right. So let's do the addition. What is 1 plus 1? Careful. 0, carry a 1. Because remember, we're working in binary now. What's 1 plus 1? 0, carry 1. And what's going to happen? A cascade of zeros, and then a final carry, which I will dispose of. And what do I get? Okay, 64 zeros in a row. Okay, so does that convince us that this number actually is -1, or that this number genuinely should represent -1, okay, as a signed integer? You're not convinced, Jaden? Are you going to be my doubting Jaden? Okay. Okay, so we have a bit of a problem. Let me go back to the pie. And our problem is this. Let me go back to my assembly, and let me change this number to -1. And let me reassemble it. Let me come back over here. A bit of a problem. How do I fit 64 ones into a command that can have at most 32 things? I can't. The other thing is, you guys noticed that something changed when I changed -1, or sorry, the 5 to a -1. Anybody spot it? Look at the instruction encoding. 80D2 suddenly has become 8092. Something's happening there. These are actually two different machine instructions. Does it look like they're the same instruction? Because it's a move instruction. So should they have the same operation code? But they don't. And that mystery I shall reveal all on Thursday. Okay. All right. See you guys later.